Hi, I'm Harsha, and today I'm going to talk to you about a small portion of the work that I did for my PhD. I study thermal ecology of pikas. Pikas are these cold adapted high elevation specialists that are currently being threatened due to climate change in the Himalayas and elsewhere in the world as well. And the idea, oops, and the idea here is that a lot of ecologists seem to think about why species are going extinct and how we can prevent them from going extinct. And one way to look at this is to understand how species have dealt with climate change events in the past and be able to extrapolate to what might happen in the future. The Earth has had complex glaciation events through its history, through the Pleistocene glacial cycles, when at particular time points the Earth was very warm and corresponded to ice sheets melting, called interglacial periods, and at other time points when the ice sheets were expanding at particularly cold time periods, called the glacial maximums. And here's a reconstruction of what the Earth looked like during the last glacial maximum, and you can see that it's mostly ice sheets. So how do we expect that cold adapted high elevation specialists respond to such large scale climate change? We expect that pikas track cool habitats and they go up the elevation gradient at particularly warm time points like the last interglacial, and expand to lower elevations as well during cold time points like the last glacial maximum. When pika populations experience particularly long interglacial periods, they get stuck on mountain tops and cannot outbreed, whereas a rescue glaciation event can basically expand pika populations to lower elevations, connecting across mountains and allowing them to outbreed. And there is evidence for such ideas from both fossil records and projections of these bioclimatic niches into the past. So pika should have large population sizes at LGM, but how do we measure population size? You can measure population size based on metrics that use genetic diversity, and a single genome is surprisingly informative. And modern genome assemblers capture this variation that you see in genomes and have at least information about two different individuals. And the idea of the PSMC is based in coalescence, that all genetic variation in a finite population is lost over finite time. So if you start with a population of 20 different individuals at present time scales, the question corresponds to how long do you have to go back in time for all of these individuals to coalesce, or for you to find a common ancestor between all of these individuals. And it turns out that is dependent on the rate of the coalescent events, but you could replace the individuals with, say, different alleles or different loci that don't recombine, basically separated by recombination breakpoints, and you could ask the same question. And it will turn out that the TMRCA is variable across the length of the genome, with some fragments being particularly young and some fragments being particularly old. And so does the recombination rate. And the PSMC is basically a mathematical relationship between the rate of the coalescent events and the effective population size. And if anybody has questions about this, I'd be happy to chat over tea. And you get something like this. So you have effective population size on the y-axis and you have time on the x-axis, with the closer to origin being current time scales and further away from the origin being going into the past. So do pika populations have larger population sizes at LGM? Just to orient you, effective population size on the y-axis and present towards the origin and away from the origin going into the past. And what we know of average climatic models that have been built of paleoclimate seem to suggest that the last interglacial was particularly warm, the last glacial maximum was particularly cold, and the middle Holocene there was a small warming event. And I sampled these three species in Ladakh, the Nubra pika, the large-eared pika, and the Ladakh pika. And all of these genomes came from the Changtang, which is the easternmost spur of the Tibetan plateau that comes into India, and this is about 4,500 meters in elevation. And I sampled one genome for each of these species, and two of these genomes were sequenced for the first time. And you get a picture like this. I expected that pika populations would peak at the LGM, but they rather peak at a much older time point called the MIS6, predating the LIG. And while the population sizes crash post the LIG, they're simply not recovered by the LGM. And these are interesting patterns that don't corroborate with what we know of what happened to global climate. and require further investigation. A large amount of data, geologist-driven data that look at moraines on the Ladakh landscape is coming through, and this seems to paint a different picture of what happened on these landscapes when compared to the global averages that are generated using these paleoclimatic models. And these look like this. It turns out that on the Changtang, the MIS-6 was the major glaciation event, and ice sheets expanded a lot, and the LIG was particularly a warm time period. The last local glaciation event on the Changtang was between MIS-3 and MIS-4, predating the LGM, and when the rest of the earth was cooling during the LGM, ice sheets were barely moving on the Changtang. So it seems like pika populations are indeed tracking local glaciation events, and this can be further corroborated with looking at vegetation communities by say looking at pollen or paleontologist driven data, and there have been at least 5 different oscillations between steppe and juniper forests between 30,000 years and 11,000 years. Steppe being a good indicator of particularly cool climates, and juniper forest being a particularly good indicator of warm climates. And during the LGM, it was particularly warm, and you had lots of pollen records of juniper vegetation and marshy vegetation even in lakes. So it does look like the pika populations are tracking local glaciation events. This is very nice. There are lots of problems, however, to generalizing the PSMC patterns that you see to the species as a whole. And this has problems to do with population structure, purifying selection, non-recombining segments of DNA, choice of mutation rate, and generation time that seem to scale these plots. But the point we're trying to make here is that we're not trying to generalize the patterns that we see to the species, but rather to comment on the fact that we sampled 3 different populations of 3 different species, and they come from the same region but seem to have similar trajectories. And what we speculate might be happening is something like this. During the MIS-6, when it was particularly cold, pika populations occurred along the elevational gradient. They got pushed up during the last interglacial, and they remained isolated on these mountain tops since the LIG because a rescue glaciation event never came. And we suspect that pika populations today might be inbred as a result of historic inbreeding that might have happened. So to summarize, these coupled GCM models used to generate these paleoclimatic models don't often reflect what's happening at local climates at high elevations, and this seems to be true across different mountain chains like the Alps and even in the Rocky Mountains. And integrating work by geologists and paleobotanists are super useful while evaluating historical demography of species like this. And some of the pika populations that we might have sampled have very low effective population sizes today when compared to the past. And they seem to largely follow these local glaciation events. I'd like to thank ISA Tirupati for funding this work, the Ladakh Forest Department for giving us permits, ISEB for giving me this opportunity to talk here, and TIFR Hyderabad, where I am currently at, for funding travel to this conference. Thanks.
Thank you, Harsha. The next presenter is Dr. Sudipta Tang from Ashoka University.